In this section, we're going to talk about the definite integrals. Now, coming to this section, we already discussed the idea of finding the area under the graph of a function, a positive function that was, and we had a number of assumptions that accompanied such a discussion. In this section, we're going to relax some of those assumptions when we talk about the definite integral. So here are the four modifications to the assumptions that we make. Number one, the function, we required the function to be positive before when we discussed the area under the curve. We no longer require that to be true. It could still be positive, but it need not be positive. It could be positive or negative. Okay, so that's the relaxation of that first assumption. And of course, when the function is negative, we no longer have the idea of area under the curve. It turns out that would be like the negative of the area under the curve. Number two, the function may be discontinuous. Okay, so it may be discontinuous at some number in the closed interval from a to b, as long as there are finite number of discontinuities, when we may be able to evaluate the integral still. Now we could have various types of discontinuities which we will address. Remember, we have removable, we have jump, and we have infinite discontinuities which can be addressed. The third requirement was that the length of the subintervals, the kth subinterval, x sub k minus 1 to x sub k, they may be different now. Okay, before we required equal length, right, actually equal width, if you will, of the subinterval. We no longer have to have that. They can be different. And finally, the evaluation points, c sub k, that we used before, it was either the left endpoint, the right endpoint, or the midpoint of the interval. Well, we're going to relax that also. It turns out that it could be any evaluation point inside of that subinterval. Okay, so with that in mind, let's now proceed with our definition of definite integrals. So the definite integral is defined as the following. If a function is continuous and defined on an interval from a to b, and if we assume that the interval is divided into subintervals of length delta x given by b minus a over n, we still assume equal widths. And what we're looking at here is actually in this segment, we're looking at a just an interval from a to b. Okay, and then you have these variables, x sub 0, x sub 1, x sub 2, all the way x sub n. These are actually like the marks that separate the cutoff for the subintervals of that interval from a to b. Now the c's that you will see in the next line, these c's, c1, c2 through cn, these are arbitrary points. Okay, so they don't have to be in the right endpoint, left, or center point. They still could be, but they need not be. So that's what the c's are. Okay, and then here's the definition of the definite integral. The definite integral is the integral from a to b of f of x dx, and then which is defined as the limit of a sum. The limit of a sum. That's the limit as n goes to infinity of the sum of f c sub k delta x. And again, we looked at those kind of limits in the previous section. Now that limit of the sum, this portion is called a Riemann sum. A Riemann sum named after Bernard Riemann. Okay, so that's what a Riemann sum is. So the definition is the limit of the Riemann sum. Now, in this section, we're going to interpret these definite integrals in their geometric form. Okay, so we're not going to show you how to actually evaluate the definite integrals until the next section when we talk about the fundamental theorem of calculus. Okay, so in this section again, we just want to give you a geometrical interpretation of the definite integral and the one that you're seeing. First of all, to give you an example of the link between the limit of the sum, the Riemann sum, and the definite integral, so you can see the similarities between them. Again, this stems from the definition we just went over. So if we have the limit as n approaches infinity of sigma of square root of 1 plus c sub k squared delta x, well, in the definite integral form, delta x transitions to dx, you still have the square root function, and c sub k just becomes x. And the limits of summation, the lower limit is 1, upper limit is n here, right? That will not show up in the definite integral. So how do we know it goes from 2 to 5? The part that we don't see here is that this limit of sum is defined over the interval, closed interval from 2 to 5. So that's actually what determines the lower and the upper limit of the definite integral. Okay, so again, those limits on the integration, you don't see them in the limit of sums. Okay, they are given by the length of that interval. It's given by the interval that's provided. Okay, now geometrically, here's a sketch of what is going on. So suppose I have a function here, and if the function is positive, again, notice we can label this as A as the area under the curve. So the definite integral actually finds the area of this region, right, of the shaded region. So that's what the definite integral from A to B of f of x represents. Again, it's important that the function will be positive so we can relate it to the area. Eventually in this section, we would want to kind of separate the area, the idea of area, from this ultimately. So let's take a look at, we're going to see some properties of these definite integrals, and then we'll look at some examples actually from the book. So the first one says or reads that the definite integral from a to a of f of x dx is 0. Now, if you think of this in terms of, let's say, the graph of a function, so this would be a, and notice the upper limit is also a. So really, your interval is just a point, isn't it? Right? This is closed interval from a to a. Well, that means just a single point a. And if I just think about this function f, right? And if I think about assuming the function is positive, right? The function is positive. And if I think about this as area under the curve, that would be synonymous to finding the area of this line, right? Of the line that is under the curve. Now, we all know that a line does not have an area, right? So the area of that line would be 0. So that would be the geometric interpretation of this. Okay? In other words, there is no area. And the second definition reads the integral from a to b of x dx is the same as the negative of the integral going from b to a. So here what happens is that we switch the limit, what we call the limit of integration. So we can do that. We can switch the limit of integration, and as long as we offset it by a negative in front of the integral symbol. Now remember, our intervals go from a to b, where earlier we said a is less than b, right? So this is what we have. That's why the lower limit goes here and the upper limit goes here. That would be the proper order of the lower and the upper limit. So when we go from b to a, we're going from higher to lower limit now. So to do that, we can again offset it by putting a negative in front of the integral symbol. And this does come in handy a lot of times, especially when the limit of integration are not from low to high. We can switch the limits. So for example, if I have the limit going from 10 to 3, notice 10 is higher, but I'm going from lower to upper limit of f of x dx. I can change that, put a negative, and make that in the proper form from low to high in that form. Okay, so that's an example of what we're doing here. Next, we're going to look at the definite integral of a constant function. So if c is a constant, we can actually bring c outside of the integral, if you will, but we can also keep it inside. And as far as, again, the geometric interpretation of the integral from a to b of c dx, remember, the integrand here is a constant function, f of x equals c. So that's what this is. We have a constant function. And the integral, the interval we're looking at goes from a to b. True? And the constant function is going to be a flat line, horizontal line when graphed. And if we kind of marry the graph of the function and the interval over which it appears, then it looks like, because the function in this case again is positive, I can say that's the area of that rectangular region. If c is negative, of course, then you get something that may look like this. This time this is y equals c, where c is less than 0, right? And this would be a, that would be b, and now we're looking at this area. But remember, because the function is negative now, this is a negative value, so we can't say really that's the area. We can call this negative of the area. But this definition, nonetheless, it holds. Okay? And that's what this is. Let's see. Next, we're going to look at a series of properties of the definite integrals. So our first property is the sum difference property, which we had it with indefinite integrals in the previous sections. So the integral of sum difference of, if the integrand is made up of sum or difference, then we can actually break it off into sum difference of two definite integrals. And of course, the limits of integration must be the same. The constant multiple rule allows us to bring the constant outside of the integral. That's the constant multiple rule. And number 3 reads that if c is any number inside of the interval, then the definite integral from a to b of f of x dx could be written as a to c plus b to c. And there you go. So on the graph that you're seeing here in this figure 12, that's an illustration of the third property. So you're looking at the interval that ranges from a to b, and we are interested in the integral from a to b, so we can actually break this into two segments, right? From a to c and then from c to b. Okay, so it's like breaking the region into two parts. Now sometimes we use this property quite often, this one, when there is a kind of discontinuity in the graph. Okay, and when there is discontinuity, we usually break this. C would be the point of discontinuity here. And of course, those will be handled in the second semester calculus, where the integrand has a finite number of discontinuities. But for us, think of it as a property. Now, an important note here, by the way, is that the conclusion of the property number 3 holds for any three numbers a, b, c. So they don't have to be really in that order. They don't have to be in the order a, b, c like that. Okay. And the fourth property tells us that if the function is positive on a closed interval, then the definite integral has to be positive. See that? The definite integral will be positive. Property number 5 tells us that if we have two functions and one is greater than the other, so f is greater than g means on the graph of function f sits above function g, lies above function g. If that's true, then over the same interval from a to b, the definite integral from a to b of f would also be greater than the definite integral from a to b of g. Okay, and again, if the function is positive, you can think of it, and we have the graphs here. This one in particular, this one. If the functions are positive, notice here f is greater than g in this drawing. So if I think in terms of the area under the curve, let me use a red for the red function g. So this would be the area under the graph of g. That represents the definite integral from a to b of g of x. And the other one, this one, would be the graph under the curve for y equal f of x. So you can kind of see that we are over by the shaded area that I just outlined here, right? More closely or exactly. There you have it. This is the extra piece of that area. So that's what this is saying, number 5. Okay, and number 6, the way this one reads is that if the function is bounded between little m and big M on a closed interval from a to b, then if you do m, the lower limit, m times b minus a, that area, if you will, or that value is going to be less than or equal to the definite integral fx dx, and that is going to be less than the value of capital M times b minus a. Now, again, for a positive function, let's illustrate what that means. Notice capital M here bounds this function from above. See, it's bounded above, means there is no value higher than that of the function. And little m bounds it below. So there is no value below that. So it's bounded below. Bounded above and bounded below. Okay. And so let's see. If I look at m, I'm looking at the left, the lower limit of that inequality, m b minus a. Well, b minus a is the length from stretching from a to b. Little m is the height, right? Is the height of this rectangle, right? So think about it as this area. So what we're saying is that that area is going to be less than or equal to this area. You see that? The area I just shaded indeed includes this part. And this is length times width kind of area because it's rectangular. So that's what that is. And of course, the larger rectangle is this is the height. Capital M is the height right there, and the distance from A to B is the length. You see that? And this area now exceeds both of the other ones, the previous ones, right? And in fact, this is the excess, if you will, as opposed to the definite integral from a to b of f of x dx. Okay, and this is what I mean. See, this is the area under the curve, right? The area under the curve is that, and of course the area of this a rectangle of height m, base b minus a. That is going to be right in here. This would be the additional area right in here, right? So anyway, these are just geometric interpretation of these properties. Okay, and now we're getting ready to define the limit of a Riemann sum for general partitions. So in this piece, we're going to talk about a partition of an interval. Okay, so a partition is any breakdown of the number line between two numbers. Okay, so for the kth subinterval, well, the length of that subinterval is going to be delta x, right, sub k, and it's given by the distance from x sub k minus 1 to x sub k, and that's how this is found. Okay, now if we partition the number line, so in our partition here, notice you start from A and you end with B. So partition goes from A to B. We're looking at a closed interval from A to B. And the way these x's occur, x sub 1, sub 2, and so on, it's such that, notice, I have different varying sizes of subintervals. This is the kth one. This is the kth subinterval. Okay? This symbol means a break in the number line. You can think of it as dot, dot, dot. Okay, that's what those symbols mean. Now, again, what's important is that we're looking at a partition that is not divided equally between the subintervals. Okay? Now, when that is the case, we can say that P here is what we call the norm of the partition, P for partition, and then the double vertical lines like this means the norm. The norm, think of it as the magnitude, okay, the magnitude of that subinterval. So for instance, let's say I have 3 intervals here. I start from 5. Okay, I go to 6, then I go to, 9, and then I go to 9.5. Okay, so the length of this piece is 1 unit long. This subinterval here is 3 units wide, and this one is 0.5. The longest subinterval runs from 6 to 9, right? Is that right there? So we say that the norm of this partition is 3. It's the distance from 6 to 9. It's the length of the largest subinterval. Okay, that's what the norm is. Now, if the partition is a regular partition, that means you divide the number line into equal parts. So for example, I go 5, 6, 7, 8, 9, 10 now. I can't go to 9.5, then it won't be regular. And there you go, good enough. Each of these are of the same width. Okay, so this would be a norm. It would be a regular partition. And in the case of a regular partition, the norm is just delta x, right? Because they're equal. And that's what this piece is telling me. Now, if the lengths for the subintervals are the same, then when we say the norm approaches 0, as the norm approaches 0, that means delta x approaches 0, true? And for delta x to approach 0, that means I have to create smaller and smaller and smaller subintervals, right? So that means the number of subintervals have to approach infinity right in here. Okay, now this is true for a regular partition. If we don't have a regular partition, so for something like up there, the converse of this statement is not true. So if the partition is not a regular partition, as n goes to infinity, the norm of the partition may not go to 0, which is kind of awkward. It's like doesn't make sense, but you can make up examples where I believe in the book there is an example of it where this is not true. They make it n go to infinity, but the length of the norm of the partition, I should say, does not approach 0. Okay, so but our focus is going to be for now on delta x here, and then we'll generalize this in a moment for any partition. So for now we are assuming we have a regular partition in this definition. So this is a more general definition of the limit of Riemann sum, of the definite integral. Okay, so this time notice f is a bounded function. A bounded function, we already saw an example of it. So for example, let's say I have a function like this, that is, and this is m, the value m. We say that this function is bounded, means it will not exceed. So f would be less than or equal m. M is a bound here. Okay, an upper bound in fact. And we could have lower bounds and so on. So as long as f is bounded, means it doesn't exceed some positive number m. Okay. Defined on an interval from a to b, so this would be, let's say, from a to b here. Okay. On a to b, then the definite integral of the function f on a to b is determined by what the notation we had before, which is now the limit of Riemann sum. So what's different now is, if you note one thing here, is we don't have the limit as n goes to infinity. This same definition is stated as the norm of the partition goes to 0. Okay, but remember, because we are using delta x, so this assumes we have a regular partition. And the regular partition, for norm to approach 0, then n must approach 0. So this is really equivalent by saying n has to approach infinity. It's based on what I have here, right? Okay, and if the limit exists for all partitions of P, okay, so doesn't matter, any partition would work. So in other words, you can break down your interval into however many pieces you want. Delta x really doesn't matter what the delta x is, as long as delta x approaches 0. Okay, so, and again, for a regular partition, the norm of the partition approaches 0 if and only if the number of sub-partitions approach infinity. That means, this part means you break it into, instead of, for example, breaking the interval from a to b into 1, 2, 3 equal parts, I break it into, I don't know, there we go, 5 equal parts. 1, 2, 3, 4, 5. Or break it into 10 equal parts. Then break those finer and finer and finer. There you go. It's a limiting process. So the limit of these will give you the limit of the Riemann sum based on these partitions that are divided into infinitely many pieces. Will give you the value of the definite integral, the exact value of the definite integral. Okay, and there we have it here. And notice again, these two statements are the same. The only difference is the limit here versus the limit here. One implies the other. It's an if and only if, means if n goes to infinity, this has to go to 0. Okay, that's from right to left. If the norm of partition goes to 0, n must go to infinity. That's going from left to right. Okay. Now, we're going to finish this with a precise definition of the definite integral. Now, the precise definition, it's kind of like, it is not kind of like, it is your delta epsilon definition of a limit, because it's limit of a sum. So we're looking at a rigorous definition of definite integral. So the definite integral from a to b fx dx written in this form. Okay, this is where we have for every epsilon positive, means there is a number delta, so that for every partition of the closed interval from a to b with the norm of the partition less than delta. So in other words, this is what we're saying. The norm of the partition lies between 0 and delta for that. And every choice of points, c sub k, remember these points, these are what we called evaluation points, right? Evaluation points, right? That's what those are. For any choice of evaluation point inside of the kth subinterval, the inequality holds. This inequality holds. There you go. Okay. This time we don't have like f of x minus L. Remember that? We had less than epsilon. We don't have it in that form. Well, it's pretty close, because again, this is equal to our L, right? And the definite integral is the limit of Riemann sum. So this is what L is. This is actually L. And we don't have just a function. We have sum. We have sum of fck delta x. Okay, so there is the rigorous definition of definite integrals. Now, let's take a look at some exercises, see what kind of exercises we could come across here. So I'm just going to bring some exercises into this document now. Okay, so here is the exercise that we have, numbers 3 through number 6. The question reads, you are given a function f defined on an interval from a to b, the number n of subintervals of equal length delta x, b minus a over n, and an evaluation point c sub k inside of that interval. In part A, sketch the graph of the function and the rectangles associated with the Riemann sum for the function f on a closed interval. And in part B, we actually want to evaluate, we want to find the Riemann sum. Okay, so this is a basic sign, so you can actually do this by hand. Remember our sine function, right? It looks like that. So I can just draw this by hand also, and we want to go from 0 to 5 pi over 4, right? The upper limit. So this part of the graph we don't need, but I just wanted this to come out nicer so you have a good understanding of the visual of what's going on with this work we're doing. So I graphed it in Desmos. And then we have it from 0 to pi over 4. Now remember, the lower limit is a, the upper limit is b. The lower limit a is your x sub 0, right? And the upper limit is your x sub n, if you will. So in this case, x sub 5 would be. Okay. So let's find out our delta x here. Our delta x, we're going to go with a regular partition. Negative b minus a over n. Okay, we were told that, right? We want equal subintervals of equal length. So b, which is 5 pi over 4 minus 0, divided by 5 rectangles. So if you invert and multiply this, we get 5 pi over 4 times invert 5, you get 1/5. The 5's divide out, and we get pi over 4. Okay, so that's going to be each delta x. Each delta x is pi over 4 units. And we are also told to use evaluation point, the right endpoint in number 6, right endpoint. So we go to pi over 4, that's our evaluation point. And then we're going to go up until it touches the curve, and then we're going to go to the left. So this will be our first rectangle. Okay. Notice we are overestimating the area because it goes above the function. Another pi over 4 puts us at pi over 2. We're using the right endpoint of that. The right endpoint tells you where to actually draw the height of that rectangle. And we're going to extend it to the left until it reaches the lower limit of that interval, which is pi over 4. Don't go all the way here. Okay. And then we're going to shade this one. So it looks like this rectangle 2 by that much overage, right? The excess. But that's what that rectangle is. So the first two rectangles overestimate the area. Now at 3 pi over 4, that's another delta x. Again, we go up until we cross the curve. It touches the curve at the point you just saw up here. You extend to the left. And this rectangle is actually underestimating, right? It's underestimating by that region. So we're hoping that these overage and underages kind of even out themselves. Now this next one is interesting. We go pi over 4, it gets us to pi. And notice at pi, the function crosses the x-axis. So you just stay at the x-axis here. So you go to the left. There's actually no area associated with that particular one, right? Because you're at 0. So there's no rectangle to draw there. And at 5 pi over 4, again, this time I have to go below, because if I go above, there's nothing up there, right? There's no curve. I have to come down to touch the curve. And it touches the curve about here, right? So again, we're going to extend this until we reach the lower limit of the interval, which is at pi. And this one right there. Now the area would be, again, remember, for when the function is negative, we have negative of the area. So this is now the excess. All of this is overage because that sits above, if you will, or I should say below the curve. The region must be bounded between the function and the x-axis. Okay, and there you have that one. So in other words, the original, if I was to paint it, there you go. This is the actual area that's bounded between the x-axis and the function. This is what we want to find out in that subinterval. And when we use the rectangle, see that rectangle, this much, this is the excess, right? The extra. But that's okay. Again, I just want to show you how that works when the function is negative. So I'm just going to draw the rectangle, and then this will be the area that we're interested in. So that addresses part A. We sketched the graph and the rectangles associated with the Riemann sum. Now, in part B, we actually want to find the Riemann sum. So for part B. Now, in part A, remember this is like x sub 1. This is x sub 0, x sub 1, x sub 2, x sub 3. This would be x sub 4, and here's x sub 5. Right? And because those happen to be our evaluation points, the right endpoints, so they become the C's that we need in our Riemann sum. Okay? So I'm going to go for this one. The Riemann sum starts with, starts with 1, 2, 3, 4, like that, right? So this would be my C1, C2, C3, right? My evaluation point. This would be C4, and this is C5. Okay? The evaluation points are inside the interval from 0 to pi over 4. Okay, we're good. Now we just have to do the Riemann sum. So I'm going to actually write now the Riemann sum for this is, call it R for the Riemann sum. That would be the sum k from 1 to 5 now, true, of f at c sub k, the evaluation point, times a delta x, right, by delta x. And this means we have to do, when k is 1, this is c sub 1, right? So that's f at c sub 1 was at pi over 4. And because delta x, we have fixed length subintervals, right? So we can actually bring this outside of the summation. It's independent of k, right? Or each width of this rectangle, each width is pi over 4 units. So that acts as a constant. And in fact, let me do that. So this is going to be pi over 4. That's our delta x, right? Then we have f at pi over 4 plus f at the next evaluation point is going to be at pi over 2, right? I'm looking at these evaluation points here. Okay, f at pi over 2 plus f at 3 pi over 4 plus f at 4 pi over 4 plus f at 5 pi over 4. Okay. And then I just have to plug them in and evaluate them, and we'll be done. Now f at pi over 4, remember the function was 2 sine x, so that's 2 sine of pi over 4 plus 2 sine pi over 2, and so on. 2 sine 3 pi over 4 plus 2 sine of pi, and finally 2 sine 5 pi over 4. Okay, and then we're gonna plug those in. Now, sine pi over 4 is root 2 sine of 45 degrees, right? That's root 2 over 2, so that's just root 2 times 2 in front makes it root 2. Plus sine of 90 degrees is 1, so that's 2 times 1. Sine of 3 pi over 4, right? 3 pi over 4 sine is positive. Root 2 over 2, so that's another root 2. Sine of pi is 0, right? Notice at that point the area, which is width times length, that's going to be 0. And that is at pi. That was the contribution of this rectangle. Remember, there's really no rectangle, there's no height. The height is 0, and you can see it right here. And finally, the contribution from that last rectangle. Now, before I write it, notice we expect this to be a negative contribution, right? Because it's below the x-axis. And sine of 5 pi over 4, the reference angle is 45 degrees. And sine is negative, right, in the third and the fourth quadrant, right? Both of these we have negative. So that's going to be times negative root 2 over 2. Okay, which means negative root 2. You see, that's consistent with our graph. All said and done, this would be pi over 4. The negative root 2 and root 2, those add to 0. So I just have 2 plus root 2. 2 plus root 2. And square root of 2 is about 1.4-ish. So this would be 1.4 plus 2, 3.4 times pi divided by 4. And on my calculator, I get about 2.7 for the answer here. Okay, and there you have it. That's part B of that exercise. Okay. So the Riemann sum, which would be equivalent to what we just found, is this. We're saying the definite integral from 0 to pi over 4, right? 0 to, actually, I'm sorry, to the upper limit of the interval was 5 pi over 4. of 5 pi over 4 of 2 sine x dx. This is approximately, is what we just found. That's approximately 2.7. It's not exactly 2.7 because we did not use the limit of Riemann sum. We only used a finite number of rectangles in a sub-interval. Okay, and there we have it. We're done with this one. So you can try some of these other exercises. Let me bring in more exercises and we'll do more of this work. Okay, in this segment, exercise 7 through 12, let's take a look at a couple of these. In exercise number 8, the question reads, use equation 2 to evaluate the integral. Now, equation 2 actually is this equation. It is the definition of definite integral using limit of the Riemann sum. Okay, so that's what equation 2 is. That's equal to the limit as n goes to infinity of the Riemann sum. Okay, limit of the sum of f c sub k times delta x. So we're going to stay with a regular partition. Okay, and for this work, k goes from 1 again to n. Okay, now and delta x is going to be the same. Now, we are not told, remember c sub k, these are evaluation points, and we are not told which evaluation points to use. Do I use right endpoint, midpoint, left endpoint? Let's take a look at something here. If I look at whatever this curve is, okay, here's x. We're looking at x sub 0 equals a. And this would be, let's say, x1, x2, and choosing these to be equal length, right? All the way up to x sub k minus 1, and this would be x sub k. Okay, now here's what I want to do. I want to look at the relationship between the sub-interval, okay, and delta x here. So remember, each of these will be a delta x. Okay, delta x, and so on, all the way up to the very end, which would be x sub n equals b. That would be this point right here. Okay, now for the first rectangle, I have 1 delta x. So when I go to x sub 1, if my evaluation point is the right endpoint, to get to that right endpoint, I count 1 delta x. The right endpoint of the second rectangle, to get to that right endpoint, I count 2 delta x's, right? And to get to the right endpoint of the third rectangle, we count 3 delta x. Well, you get the idea, right? To get to the right endpoint of the fourth, I'm going to have to count 4 delta x's to reach that point. So for the kth, this is the kth sub-interval, right? So that would mean this is my kth rectangle. Yeah, once we construct the rectangles, right? It would be my kth rectangle, right? How many delta x's to get to x sub k? Well, in this case, x sub k is going to be k delta x's, right? If I use the right endpoint, it will take k delta x's to reach from a, the starting point, to x sub k. So we're going to use this in this segment. So in exercise number 8, here we go. Note that a is the left endpoint of that interval from a to b, and in this case b is 2. Correct? The interval runs from -1 to 2. Okay, so I need to figure out my delta x's. B minus a over n. B is 2 minus -1 over n, notice I don't have a number for n because n goes to infinity, right? The limit as n goes to infinity. So that's going to be 3 over n. This is what our delta x is. So each delta x equal width, they're going to be 3 over n. Now, in order to get to x sub k, right, x sub k, I have k delta x's from a, right, from a, but a was -1. So I start at -1 and then count k delta x's to get to x sub k, don't I? Okay, and I can replace delta x now with 3 over n, right? So my x sub k is therefore -1 plus k times 3 over n. Okay, and so on. And of course, remember, x sub n is going to be b, which in this case is 2. Okay, now I'm not saying this is the graph of the function, right? I know that's a parabola. In number 8 we have x squared, which is a parabola. I'm just using a general curve. The curve itself doesn't matter. What mattered is that how do we think about the relationship between x sub k and how many delta x's it takes to reach there. Okay, good. And then what do we need to do next? So my evaluation point, our c sub k, we're going to go right endpoint. In all of these you can go right endpoint. It's just easiest in terms of k delta x here for x sub k. If you go left endpoint, by the way, then you go to x sub k minus 1 equals how many delta x's? K minus 1 delta x. That would be your left endpoint. This is for left endpoint. But again, I like to use the right endpoint. But you could try left endpoint like that. In the limiting sense, it doesn't make a difference because we will take the limit anyhow. Okay, so c sub k is going to be the right endpoint. Okay, inside the interval x sub k minus 1 to x sub k. For any, this means for any subinterval, the evaluation point would be the right endpoint. Okay, so therefore the definite integral from -1 to 2 of x squared dx is going to equal to the limit as n goes to infinity of the sum k goes from 1 to n of f at c sub k delta x. Now, before we get really down to doing this is going to be messy. Okay, and let me also mention, this is my integral, right, is going to be. This is not how we want to find definite integrals going forward. Okay, but it's just kind of like a learning curve, right? It's like kind of growing up. These are the growing pains. Okay, but it just shows you how definite integrals are defined in terms of limit of Riemann sums. But we would like to have other ways of doing it. The way we're about to do it, it's very harsh, it's brutal. We don't want to do it this way. It works, but we don't want to do it this way. So going forward, don't worry, we don't have to do this. It's a passing phase. Okay, we will do it in the next section. In fact, we will see how we can do this without using the limit of Riemann sums. Okay, so let's continue on. So this is going to be the limit as n goes to infinity, k goes from 1 to n of. Now, f at c sub k, remember our function here, f of x is x squared. That's the function in the integrand, right? F at c sub k means you plug in c sub k for x squared, but what was our c sub k? Our c sub k is going to be this, except you change, and that's what that is. Instead of x, you have c sub k. Okay, so it's going to be -1 plus 3k over n, right? That was our x sub n. squared times 3 over n, which is delta x. And remember, we did this kind of limit back in section on area. So I'm going to go limit as n goes to infinity. 3 over n could be moved outside of the summation because the variable of summation is k. It's independent. N is independent of k. And then do sum as k goes from 1 to n of parentheses. Now we're going to expand the binomial. Right, when we expand the binomial, first one squared plus second times first by second, right? That gives me twice negative 1 by 3k over n. That's 6k over n. Plus the second term squared makes this 9k squared over n squared. And there we have inside of the parentheses figured out. Next, I'm going to write this as limit as n approaches infinity of, stay with 3 over n. Now, we're going to expand, right? We're going to expand the sigma here. In other words, what I mean by expanding is we're going to write it as 3 separate sums. So that's going to be sigma k1 to n of 1, negative 6 over n comes outside, sigma of k. We've done this kind of sigmas again in previous sections, so it should be familiar to you. 9 over n squared, right? We're going to factor that out, bring it outside of the summation. Anything that doesn't have k in it, we can bring it out. k1 to n, and there you have it. Okay. So this will equal to the limit as n goes to infinity of 3 over n. And remember the properties of summation. The sum from k goes from 1 to n of a constant is n constant. So that means my first is n times 1, right? Negative 6 over n. Now sigma of k, the formula we had for this one from 1 to n was n plus 1 over 2, right? So I'm just going to write this times n plus 1 over 2. That replaces the sigma. And then plus 9 over n squared times sigma k squared. The formula we had for sigma k squared was n plus 1, 2n plus 1 divided by 6, if I remember correctly, as k goes from 1 to n. So this one it's going to be n plus 1, 2n plus 1 divided by 6. All right, and there you go. So I have 3 sigmas and I have 1, 2, 3 equivalent form of those. Now let's take, remember the way to do this, do not worry about combining like terms, combining fractions and all of that stuff. It just takes too long and we're going to get lost in the work. So I'm going to take the limits one piece at a time. Let's look at that piece. So the expression is 3n over n. The limit as n goes to infinity of that is just what, 3? And there you go. That's our first limit. Then I'm taking the limit of this expression. Remember, there is a 3 over n on the outside. So that's going to be negative, right? 3 by 6 is 18. N times n is n squared plus whatever. We don't care about the leading terms, the other terms, not the leading terms, but the successive terms. In the denominator, I have 2n and n. That's 2n squared. There you go. That's all we care about in finding this limit. Again, the reason is because as n goes to infinity, the first term in the polynomial dominates the behavior of the polynomial. So it doesn't matter how these do. All of these kind of go to 0. when you divide it by 2n squared. Okay, so the ratio now of 18 to 2, that's going to be -9 because the n squares cancel, so that ratio is -9. There is the second limit. And then I have to find this limit. Remember, there's a 3 over n in front of it. So the denominator is going to be 6n cubed, right? The numerator, I'm going to have 3 times 9, right? It's 3 times 9, 27, and then the 2. So the constants here are going to be 6 times 9, 54, right? That's 3 by 9 by 2. And then the n by n by n, those multiply to n cubed plus whatever the follow-up terms would be. Okay. Now, let's see. We can divide by n cubed. Those cross out. All of these terms, when you divide by n cubed, approach 0. All the ones that I haven't written. Now 54 divided by 6 will be 9, so that's plus 9. And the limit is 3. Let's see how that worked. So again, this is much better alternative to trying to simplify inside the bracket. We don't want to do that. All right, and let's see. Number 8, so we're good. We're done with number 8. And again, as I mentioned, we don't really want to do this. We don't want to do this when we evaluate definite integral. That's just very tedious, very cumbersome. So we will look at, in the next section, when we look at the fundamental theorem of calculus, that's going to be godsend for us, right? Because it will prevent us from doing this. Let's take a look at number 12 in this work. So again, you might want to pause the video, take a break, go get something to drink, rest even, maybe take a nap, come back and watch the rest of the video, because this is going to be another similar problem like the one we did. Okay, and I'm going to use the right endpoint in this one. So the function x cubed plus 2x from -2 to 1. Okay, so our delta x, first of all, is going to be 1. That's b minus a divided by n. It so happens is 3 over n because the way the interval from a to b works out. Okay, now I'm going to use the right endpoint, remember? So my x sub k is going to be the initial point a plus k delta x's, right? Okay, so that means it's going to be -2 plus k times 3 over n. That's why I like using the right endpoint, because you always end up with k delta x from a. In general, if you want to know, that's a plus k delta x if you use the right endpoints. Okay, now therefore the integral from -2 to 1 of x cubed plus 2x delta x is going to equal to the limit as n goes to infinity of the Riemann sum k1 to n of, this time remember, x sub k becomes c sub k, because that is, remember, this is x sub k minus 1. This is x sub k. This is my kth subinterval. If my evaluation point is the right endpoint, that means ck, c sub k, and x sub k coincide. They become the same. Okay, so I can actually use c sub k right in here instead of x sub k. Okay, and let's see, let me just, so I have more space, let me move this down below. So this is going to equal to the limit as n goes to infinity of the sum k from 1 to n of, now I'm going to plug in c sub k into x cubed plus 2x. So it's going to be negative 2 plus 3k over n cubed, right? Plus 2x, but then x sub k would be, in this case, negative 2 plus 3k over n, right? That's 2x. And then times 3 over n, which is delta x. All right. Now, we need to expand this binomial. Okay. And I'm going to do that on the side so the video doesn't run too long. But I'm going to be doing this. I'm going to be cubing a binomial, this one again. Now, if you recall from the binomial theorem, or simply the expansion of a plus b cubed, this is going to be a cubed plus 3a squared b plus 3ab squared plus b cubed, right? So I'm going to have 1, 2, 3, 4 terms in the expansion when I return, because I'm going to do this on my scratch paper and bring just the results. And then I'm going to, so I'm just going to do this one, right, on my scratch paper. This will be easy to do. 2 times negative 2 plus 3k over n. That will be easy to do. So what I want to do is I'm going to pause this video briefly, do this with that expression, okay? And I'll come back with the clean results. Okay, so I am ready. This is going to equal to the limit as n goes to infinity. I'm going to bring also 3 over n to the front. Let me put that in front. So there's my 3 over n. And then the sigma is going to be sum k1 to n. So within the bracket, it's going to become negative 8 plus 36k over n, negative 54k squared divided by n squared plus 27k cubed divided by n cubed. See, those are the 4. 1, 2, 3, 4. 1, 2, 3, 4 that I got once I simplified it. Now, plus this, actually minus now 2 times both of those terms. That makes it negative 4 plus 6k over n, right? And there you have it. So what's going to happen next? Now we got to work out all of those sigmas, right? So this is going to be the limit as n approaches infinity of 3 over n. And I'm going to write this. Let's see. I can combine some things here, like 4 and 8. That's going to be 12, right? That's going to make it 12, negative 12. So this is going to become sum sigma of negative 12. K goes from 1 to n. Plus, so I combine those two. Let's combine these two fractions. Okay, so I have 36 and 6. That makes this 42k over n, doesn't it? So I'm going to factor, bring out 42 over n sigma of k from 1 to n. Okay, so I have that one. And this is done. So remember, I now have accounted for these. The only two remain are these two. Negative 54 over n squared of sigma of k squared. K goes from 1 to n. Positive 27 over n cubed sigma k cubed as k goes from 1 to n. And you can kind of see again how convoluted this thing can get. That's why we really do not want to do this going forward. I'm just glad we're doing it in this section. Limit as n goes to infinity of, this is 3 over n. And we're going to do our usual stuff. Remember the formulas we had again? Some of them I have them up here still. right? Remember these formulas we're going to use. And we also have to use, we're going to need to use a formula for sigma k cubed. Let me write that here. Sigma k cubed. In earlier sections, we said that's going to be just like sigma k, n plus 1 over 2 quantity squared. These formulas usually for sigma k, k squared, k cubed, we don't have the students memorize these. Usually we provide to them, but if you do these, you know, long and hard enough, you can't help but to at least temporarily have them memorized, right? Okay, so the first sum is going to be this one. I'm working on this one. It's going to be a constant multiple of n, so that's going to be negative 12n, right? There you go. The next one is plus 42 over n times sigma of k, that's going to be n plus 1 over 2, minus 54 over n squared, sigma k squared, that was n plus 1, 2n plus 1 divided by 6. And the next one is for k cubed, 27 over n cubed times sigma k cubed is n. It's going to be n plus 1 divided by 2 quantity squared, right? This is right in here. And I think I've accounted for all of these, right? Yes, and because I'm using brackets, let me use braces for start and the ending. Boy, look at that one. Okay, now we're going to find the limit of this thing. And again, if you do the limit the way I do it, it's going to go a lot easier, and it's not going to be as drawn out. Okay, remember, it's your choice. If you want, you can combine fractions in that beast. I don't really recommend doing it unless you really have nothing better to do and you cannot fall asleep and you just need something to put you to sleep. So try to simplify that expression. I'm going to leave that up to you. Okay, so I'm going to choose the easier way out. What's the easier way out? I'm going to find the limit one piece at a time. So I've got 1, 2, 3, 4 pieces, right? So I'm going to try to find those limits one at a time. First one, the limit of, and remember how I'm doing this, I'm only looking at in the numerator the leading term of the numerator and then the denominator, whatever it turns out to be. Okay, so for the first piece, that's negative 36n over n. That's the easiest piece, right? The n's cross out, so that limit is negative 36. That was easy. Boom, we're done with that one. The second piece, the number multiplies 3 times 42, right? 3 times 42, and then n is n squared. So I just need the leading term, right? It doesn't matter what comes after these. Okay. The denominator is 2nn, so that's 2n squared, right? Again, the n squares cross out. 42 divided by 2 is 21, and 21 times 3 is 63. So that's plus 63. That's that limit. Okay, we're done with that limit. Now, let's take a look at the next piece. 3 over n multiplies by that. So in the denominator, we have 6 n squared, n is n cubed. In the numerator, and of course remember this is negative, so keep side of that. That's a negative, so it's going to be a negative here. In the numerator, we have 3 times 54 times 2, and then the leading term will be n cubed. And again, plus probably a bunch of terms which we don't care about, right? Now for this work again, the n cubes divide out, right? 2 by 3, 6 divided by 6 crosses out, so we just have 54 plus, and we are done with the limit of that third expression. Okay, now what do we have next? Next, our last expression is this one. Again, you have 3 over n, which distributes over the denominator. It's 2 by n cubed by n. That's 2n to the 4th, right? That's the denominator. The numerator is going to be 3 times, actually, sorry. Notice it's a square, right? So the denominator, that 2 becomes a square, that's a 4. So it's 4n to the 4th, because 2 gets squared. Got to be careful when I do the numerator with that squared also. Okay, now in the numerator, the constant 3 times 27, so that's 3 by 27, true, which is what, 81. And now n makes n squared, right? But then it gets squared again, so that's n to the 4th plus whatever that follows from that. Okay, now the n to the 4th divide out. 3 times 27 is 81, so you get 81 fourths, and that's going to be that limit for that piece. Okay, and we are good. We found that limit. Look how we did it, one piece at a time, literally. Okay, and then we need to now work this one. 63 minus 54, that's 9 positive, negative 36 plus 9, that's negative 25, right? Negative, 27, negative 27 plus 81 fourth, right? So we can do negative 7 times 4 divided by 4 plus 81 fourths, and negative 27 times 4 is 108, right? Negative 108 plus 81 fourths, and this turns out to be 27. Looks like the whole thing is negative 27 fourths. And there you have it. That's going to be the definite integral for number 12. Okay. So as I mentioned, this is not how we want to do it going forward, but this is a passing section. So, and in fact, it's the last section that we're going to do this kind of limit in. From here on, it's going to get a lot easier, folks, a lot easier. So just be patient. Okay, let me grab another piece of exercise and come back. Okay. This segment, these are actually pretty easy. Okay, let's do a couple of these. These are going to go pretty fast to make up for the previous example that took so long. So in this segment, the given expression is the limit of a Riemann sum. Okay, remember the sigma is what's called the Riemann sum. So this is a limit of a Riemann sum for the function on a closed interval from a to b. Write this expression as a definite integral on the closed interval from a to b. So exercise number 14, remember when we change these to definite integrals, so we have the integral symbol. The limit of the integral come from the interval that's given. That means they're going to go from 0 to 3 in this case, right? And what's in here, right, inside the summation, that's actually your function, the integrand. Change your evaluation point c sub k to just make it a general x. That's 1 minus x, quantity squared, and then here's dx. And there you have it. That's it. We are done. You don't have to do anything. You don't have to find the limit and do anything like that. So I did mention these are pretty easy. Number 16, let's do the same thing. It's just a rewrite. That's all we're doing, is we are rewriting those expressions. So the limit of the sum turns into the symbol, the integral symbol. Where do I get the limits of integration? 0 goes the lower limit, pi over 2 goes on the upper limit. So that's 0 to pi over 2. That's where we get the limits of integration. And remember, this is your integrand. Change your c's to x's. So it's going to be x and then cosine x, right? X cos x. And then delta x turns into dx. Remember that we had that discussion about the increment of x and differential of x. So that's what those turn out to be. Okay, and that's what number 16 is. And let me get more of the exercises. Okay, let's take a look at number 18. In exercise number 18, we're given the graph of a function. Okay, we don't know what this function is. It's just something that they've graphed. Okay, and most likely it's not a one-piece function. This is a piecewise function, because I can see 1, 2, 3, 4, 5 pieces in that piecewise function, but that's not important. The question: evaluate each integral by interpreting it geometrically. Remember, the definite integrals at this point in this section, we have two options. We can either use limit of the sums, Riemann sums, which we have been doing to find the definite integral, right? We just did a couple of examples of that. Or we can translate these into geometrically something, a region on a plane, and hopefully the region is well defined using circles, rectangles, triangles, trapezoids, things that we have already the formulas for. That's the only way we can do them in this section. Okay, so let's try number 18, part A. In part A, we want to find the definite integral from -4 to 1, right? So we're going to go -4 to 1 of f of x dx. So here's -4, this is 1. In that interval, we want to evaluate the definite integral. So I can see that area is going to be, there you go, let me shade it. So this is what we want to find. The sum of those two regions represents the definite integral. Okay, so in part A, the integral from -4 to 1 of f of x dx. Now, however you find these areas, the first one is going to be a triangle, right? So the area of a triangle is 1/2 base times height. True? Now, to make it more legible, the height of this rectangle is 2. The base of it is 2, running from -4 to 2, right? So because it's below the x-axis, it's going to be negative 1/2 base times height. Okay, plus. And then here what I can do is I can actually find the area of that shaded region. I can use the formula for a trapezoid, right? Or if you want, you can see this area, this region, as the sum of a triangle and a rectangle. You can do it that way. Okay, so if you see it as a trapezoid, there you go, that's my trapezoid. So for area of a trapezoid, it's going to be average the two bases, this one and this one, the average these two, multiplied by height h, which is 2. Okay, so that would be 1. That's this, the length of that base is 1. The length from -2 to 1 of this piece is 3. So it's going to be 1 plus 3 divided by 2. That's the average base times height of 2. So this will give me -2 plus 4, right? Because the 2's cross out. So I get 2. The answer to part A is 2. All right. And there we are done with part A. In part B, the definite integral from 1 to 5. So now we're moving forward from 1 to 5. And for this one now, I can see that as a rectangle surmounted by a semicircle, a half circle, right? So that integral of f of x dx is going to equal to the rectangular portion, base is from 1 to 5, base is 4, height is 2 units. So it's a 4 by 2, right? And then we're going to add to it the area of that half circle, this one. Now the area of a whole circle is pi r squared. The radius here is 2 units, right? So it's going to be pi times r squared. That's 4 pi, right? And then because it's half circle, you divide it by 2, not the whole circle. So that's going to be 8 plus 2 pi. Got part B done. In part C, we want the integral from 5 to 8. Notice we're just moving along the number line from left to right. So now we want to find the area of that region. Okay, again, this one I can see that as a trapezoid of its own. Here's my trapezoid. One base is 1, the other base from 5 to 8 is 3, and the height here is 2. So the area of my trapezoid is going to be 1 plus 3 divided by 2. That's the average bases. The average of 2 bases multiplied by 2. And again, that piece is going to be 4 also. All right. And that's part C. Now in part D, the question reads, find the area or the definite integral from -4 to 8 fx dx. So I guess those other parts A, B, C, what they did is they kind of moved from left to right. And here's how we can do this now. We can write this as the integral, 3 integrals from -4 to 1, that's part A, right, of fx dx, plus part B from 1 to 5 of fx dx, plus from 5 to 8 fx dx. There. And the reason we want to do that is because we have those answers from A, B, C. That's going to be A was 2, B 8 plus 2 pi, and C was 4, right? And that makes it 14 plus 2 pi. That is the exact area, 14 plus 2 pi. If you want, you can factor a 2 out, it doesn't matter. 7 plus pi, just so, because they taught me to factor everything, so that's just staying with me. All right, we're done with number 18. Hopefully that one looks good too. Okay, let me grab more and bring it over. Okay, now we're looking at exercises in numbers 19 to 26. You're given a definite integral from a to b of some function. Make a sketch of f on the closed interval from a to b, then use the geometric interpretation. Remember, at this point, this is really all we have. So if the geometry of these is such that it doesn't define a region that we recognize as like either again a rectangle, triangle, circle, trapezoid, and pretty much those, we wouldn't be able to do this. Okay, so let's do the geometry for number 22. We want to find the definite integral from negative to 2 of absolute value of x dx. Now, first I need to graph the absolute value, right? and that one isn't going to be too bad. The absolute value function is going to look like so, right? That's the absolute value function. And I know it looks like that, right? But we only need it from -1 to 2, right? That's our focus, so that's why I didn't extend the rest of it. All right, there we have it. So notice now we can translate this into 2 triangles and find these areas, right? So when x is -1, y would be 1. So the height is at 1 here. When x is 2, absolute value of 2 is 2. This point is 2, 2. The height, in other words, is 2. So let's say for this rectangle, so I'm going to call I the definite integral. I is going to be 1/2, base is 1, height is 1, right? This distance is 1, and so is the height is 1, right? Don't worry about the -1 here, right? -1, because we actually looking at the geometric figure here, so that we take the sides to be positive, because the function is positive, right? See, the function sits above the x-axis, so this is truly the area. And then for the second, the larger triangle, I'm going to have 1/2. Its base is 2. Its height is 2. So the answer is going to be 1/2 plus 2, or 5/2, right? So the answer to number 22 is going to be 5/2. In number 26, we want to evaluate the definite integral from 0 to 2 of the square root of -x squared plus 2x dx. Okay, now for this one, in number 26, what does the graph of this look like? Now, to better see this graph, let me write it as y equal to -x squared plus 2x. Okay, now I'm going to square both sides, so I get y squared is equal to -x squared plus 2x. Okay, and then we can bring the x's to the other side, so that's plus x squared minus 2x, right, equals 0. And then I'm going to complete the square in x. So when I complete the square, remember how that goes: half of the coefficient on x, half of -2, and then we square it. That's what gets added to both sides. That's going to be -1 squared is 1. So I'm going to add 1 here and add 1 here, add 1 to both sides. And then at this point, I have completed the square. So this is going to be y squared plus x minus 1 squared equals 1. And this is going to be, if I write it in the form y minus k squared plus x minus h squared equals r squared. Remember, that's the equation of a circle. That's what that is. The center is at hk and the radius r, correct? Radius is r. So the center of this circle is going to be at h, which is 1, k0, and radius is 1. Okay, so center at 1, 0, radius 1. And that's what this is going to be. So I'm just going to draw a half circle, right? And the reason it's a half circle is because you have square root. The positive root gives you the upper portion of the circle, the half circle. Okay, and the center is at 1, radius 1, so that extends it to a distance of 2 on the x-axis. And so there you go. That's the graph of the function. It's going to be a half circle from 0 to 2. The area of a circle, again, is pi r squared. For a semicircle, it's going to be a half of that, right? Half of pi, radius 1 squared. So the answer is just going to be pi over 2. You see that? Now, if we want to integrate this, actually, folks, it's going to be difficult to integrate this. Your substitution method will render useless in this case. So how am I going to actually integrate this? This kind of integral we do in second semester calculus using trig substitution. But for now, that's good enough for us. Pi over 2 is the answer, and we're done with this exercise. Okay, so let me again bring some more and we'll do more. In number 30, we are given the definite integral of some function from -2 to 2 is 3, and we're given 0 to 2 of the same is 2, and we want to evaluate the remaining integrals, definite integrals. Now, for this one, let me just do a hypothetical drawing which will help us kind of see how we're going to play around with what's given. Okay, I'm not saying that's the graph, but hypothetically, whatever the graph is, it may something like that, look like that. Now, I know this goes from -2 to 2, right, because that's what's given here. And in between, we go 0 to 2. Okay, so those two pieces of information are given. So I'm given, in other words, let's say, would be the definite integral over the entire domain from -2 to 2, and I'm also given portion of that from 0 to 2. Okay. Now evaluate the following in part A. Let's do part A. In part A, the integral from 2 to 0 of f of x dx. Now remember, the limits of integration go from low to high, right? This one, actually, the lower limit exceeds 0, so it's actually the other way around, right? So for part A, the limits are not in proper order. I'm going to switch them using the properties of definite integrals. When you switch the limits of integration, you change the sign of the integral. So it's going to be negative now of f of x dx. And that we are given. The integral from 0 to 2 was 2, so this answer is going to be -2. Okay. There's part A. That was easy. In part B, the integral from -2 to 0 of f of x plus 3, a constant, dx. Okay. Now this I can break it into two integrand, right? We're given sum. The integrand is sum of two functions, f of x and a constant function. So let's actually break this into two integrands, f of x, and then plus the integral from -2 to 0 of just 3 dx. Now remember, for the constant function, the integral of a constant dx as we go from a to b, we said that would be the area of a rectangle, right, given by c times b minus a. And that's what I'm going to do for this one, because 3 is a constant. The integral from -2 to 0 here, right? Well, -2 to 0, we can say that's going to be -2 to 2, right? The whole thing. Subtract 0 to 2 from it, right? Take this out of it, and you get -2 to 0, right? So that's what I'm going to do for -2 to 0 part. Okay. I'm going to go the integral from -2 to 2 over the entire domain, right? fx dx. Subtract from it the piece that goes from 0 to 2 of f of x dx. Okay. Again, on the graph, it would be like doing this. This is area from -2 to 2. And then we are given the area from 0 to 2. So if I subtract 0 to 2, I'm going to end up with the area that I want here, right? So that's what I'm doing. And for the last part, the latter part here, I'm just going to use the formula we have. It's going to be the constant times the length, which is b minus a, right? Now, actually, b is 0 here, right? That's b, this is a. So it's going to be 0 minus minus 2. And that's going to be positive 2. Now, the integral from negative 2 to 2, that was given to be 3. So this is equal to 3. I'm not sure what's... my pen is acting again. Okay, so that's going to be 3. Okay, minus the 0 to 2 part, that was 2. So it's going to be 3 minus 2 plus 6. So the answer is going to be 7. Okay. Hopefully you follow that. In part C, the integral of 3 times f of x from 2 to 0 and minus 0 to negative 2 of 2 times f of x. So let me write that over here now. It was the integral from 2 to 0 of 3 f of x dx minus 0 to negative 2 and then by 2 f of x dx. Okay. So for this one, let's first of all, again, the limits of integration are not in the proper position in the beginning, right? 2 to 0 should go 0 to 2. So this is going to be equal to, we change the integral to a negative integral, change the limits of integration, 0 to 2 of f of x dx, right? And we have that up here. See, that's just the 2. And the latter part from 0 to negative 2. Okay, so from 0 to negative 2, we're going to change that plus. Remember, again, it's not in proper position. 0 is bigger than negative 2, so it should be above negative 2. So I'm going to change the limits. Negative and negative makes positive. If you will, let me write it this way. This is negative. And then negative of the integral from 0 to 2. We switch them, right? So it's going to be from negative 2 to 0 of 2 fx dx. Okay, the first part, that's negative 3. We were given 0 to 2 is 2. And then bring the 2 on the outside, so that's plus 2 now. And now the integral from negative 2 to 0 of f of x dx. Right? That integral is going to be, how are we going to do that one? Negative 2 to 0. Did we do that earlier? The integral from negative 2 to 0. Yes, we did it right up here. You see that? From negative 2 to 0. And that turned out to be, we did it earlier in part B. That's going to be 3 minus 2, right? I'm just going to put 1. So this is going to be, that's going to be 1 from part B. Okay, so you can see the work for that. And we're good to go. We got all the components of it. So that's negative 6 and then plus 2 times 1. The answer is going to be negative 4. Okay, and there we have it. Hopefully, again, you follow this one. Drawing the region really helps me, so I encourage you to do the same. And let's take a look at, I think, So I think this is probably good enough for what we wanted to do in this section. We have done enough exercises. So please take a look at again these exercises that we've done, maybe just at a slower pace, and then hopefully everything will work out well. So with that, we are done with section 4.4, the definite integrals.